In this chapter, we'll define how to evaluate models rigorously, the datasets, metrics, and experimental protocols that produce fair, reproducible comparisons. We'll also cover statistical testing and common pitfalls to avoid when interpreting results. As AI systems are deployed more widely, the chance of severe failures rises because there are simply more opportunities for mistakes. We've already seen real harms. A chatbot encouraged a man to kill himself. Lawyers submitted AI-hallucinated evidence. And Air Canada was ordered to pay damages after its bot gave false travel advice. So without robust quality control, the risks can outweigh the benefits. Teams adopting AI often find the hardest work is evaluation, not model training. Defining metrics, collecting representative test data, and handling edge cases can take up most of the development effort and ultimately decides whether an application works in production. Evaluation of open-ended models is both important and surprisingly complex, so this topic spans 2 chapters. In this chapter, we'll look at the common evaluation methods, how each one works, and their limitations. The next chapter shows how to use those methods to pick models for your application and build an evaluation pipeline. Evaluation shouldn't be an isolated activity. It must be tied to the whole system. Start by identifying where the system is most likely to fail and design your tests around those failure points. That often means redesigning parts of a system to increase visibility, because metrics or tools alone can't make a system robust without a clear understanding of its failures. People often settle for hearsay or just eyeballing model outputs, but those informal checks are unreliable. Relying on them increases risk and slows application iteration. So prioritize systematic, repeatable evaluation to make results dependable. Many foundation models include a language model component, so we need scalar metrics to measure how well they predict text. Cross-entropy and its exponential perplexity are the standard choices. They guide training and fine-tuning and are widely used in language model evaluations. Foundation models are hard to evaluate because their outputs are open-ended, so human judgments are often necessary for subjective qualities. In this chapter, we prioritize automating evaluation where possible, using exact metrics and automated proxies, while recognizing that human annotators remain essential in many cases. A growing trend is using AI to evaluate other AI responses, what we call AI-as-Judge. These evaluations are inherently subjective because the score depends on which judge model and prompt are used. The method is gaining rapid traction, but many worry AI judges aren't yet trustworthy. We'll explore both the promise and the criticisms. In this section, we'll outline the key reasons evaluating foundation models is difficult. Expect to see challenges around scale, broad capabilities, data and distribution shifts, and safety and alignment trade-offs. Evaluating ML models was already challenging, but foundation models raise the difficulty further. Their enormous scale, broad multitask behavior, context sensitivity, and emergent capabilities mean single metrics and small test sets often miss important failure modes. As models get smarter, surface coherence no longer guarantees correctness. A plausible-sounding answer can still be wrong. Evaluating sophisticated outputs often requires fact-checking, deeper reasoning, or domain expertise, so validation becomes significantly more time-consuming than judging simple mistakes. In traditional, closed-ended tasks, a model has a limited set of correct answers, so you can directly compare its output to a ground truth. Foundation models handle open-ended tasks where many different responses can be valid for the same input, making it impossible to curate a comprehensive list of correct outputs. That mismatch means standard accuracy checks fail, and we must use alternative evaluation methods. Many foundation models are effectively black boxes. Vendors may not disclose architecture, training data, or training procedures, and developers may lack the expertise to inspect them. Those internal details matter because they reveal likely strengths, blind spots, and failure modes. Without them, evaluation is limited to observing outputs, which makes diagnosing errors and estimating trustworthiness much harder. We call a benchmark saturated when models reach near-perfect scores and the test no longer distinguishes capabilities. Foundation models improve so rapidly that benchmarks age fast. For example, BLEU, 2018, was effectively saturated by 2019 and replaced by SuperGLUE, Natural Instructions, 2021, by Supernatural Instructions, 2022, and MMLU, 2020, by MLU Pro, 2024. For general-purpose models, evaluation isn't just about benchmark scores on known tasks. We must both measure performance on familiar tasks and actively search for new, unexpected abilities, including ones that could exceed human capabilities, to understand a model's true potential and limitations. The rise of new evaluation challenges triggered a burst of methods and benchmarks. As Figure 3.1 shows, published papers on LLM evaluation grew roughly exponentially in the first half of 2023, from about 2 per month to nearly 35 per month, illustrating rapid community activity. This image shows an upward-sloping line, which indicates a positive trend or growth over the horizontal axis. Pay attention to the slope. It tells you the rate of change, and to where the line crosses the axis to interpret baseline values. This figure tracks how the number of papers evaluating large language models has changed over time. We'll refer to it to highlight growth patterns and shifts in what researchers test and measure. I examined the top 1,000 AI-related GitHub repositories by stars and found more than 50 focused on evaluation as of May 2024. When I plot their creation dates, the count rises roughly exponentially, which suggests rapidly growing attention and tooling around model evaluation and benchmarking. Although interest in evaluation is growing, it still gets much less systematic attention than the rest of the AI pipeline. Balduzzi et al. From DeepMind note that experiment results are mainly used to improve algorithms, not the evaluations themselves. Anthropic therefore urged policymakers to increase funding for new evaluation methods and robustness analysis. This center chart shows how a population count increases over time. Notice the overall upward trend and any sections where the curve steepens or flattens. Those features tell us whether growth is accelerating, steady, or slowing. Also check the axes and labels to interpret the timescale and magnitude. This figure summarizes how many of the 1,000 most popular AI repositories on GitHub include open-source evaluation resources. We'll examine this to gauge how widely shared evaluation datasets and tools are in prominent AI projects. There are far fewer tools built for evaluation than for modeling, training, or AI orchestration. This reflects an investment gap. The ecosystem prioritizes building and running models, while measurement and rigorous testing remain under-resourced. When teams underinvest in evaluation infrastructure, they end up eyeballing outputs or relying on a few familiar prompts. Those prompts are usually chosen from personal experience, not from the application's needs, so they miss important failure modes. That can work to start a project, but it prevents reliable iteration. This chapter teaches a systematic approach instead. This bar chart compares values across different categories. First, note the tallest and shortest bars to identify which categories dominate or lag. Then check the vertical axis and any labels for the measurement units. If one bar is far from the others, treat it as a potential outlier worth investigating further. This figure draws on my list of the 1,000 most popular AI GitHub repositories and shows that evaluation tools trail other AI engineering areas. We'll use this section to explore why evaluation is underrepresented and what that means for practice and research. In this section, we'll introduce the key metrics used to evaluate language models. You'll learn what each metric measures, why it matters, and when to prefer one metric over another. Many foundation models are built on language models, and research shows LM performance tends to correlate with how well the overall foundation model does on downstream tasks. So learning basic language model metrics gives a useful, though approximate, guide to expected downstream performance. Since Shannon's 1951 work, language model training and evaluation have largely relied on cross-entropy-based metrics. Autoregressive models are trained to minimize cross-entropy, often reported as perplexity, and BPC/BPB are character or byte-level variants that measure the average surprise per symbol. These four metrics measure the same underlying predictive quality in different units. Given one of them, and the required info like sequence length or token alphabet, you can compute the other three, and although we call them language model metrics, they apply to any sequence-generating model, not just text. A language model learns probabilities for which tokens tend to follow a given context. For example, after "I like drinking __," the model assigns much higher probability to tea than to charcoal. The more patterns it captures, the better its next token predictions become. A language model's job is to approximate the distribution of its training data. If it does this well, its training cross-entropy falls and it predicts next tokens more accurately. In practice, you care about performance on your production data. The more similar that data is to the training data, the better the model will work for your use case. This section goes into the mathematical details of the metrics, but it's fine to skip the formulas if they're confusing. Focus on how to interpret and apply the metrics. Understanding them helps you choose and evaluate models and can support evaluation and data deduplication techniques discussed elsewhere in the book. We'll introduce entropy, the core measure of uncertainty or information in a probability distribution. In this section, you'll learn its definition, intuition, and why it matters in information theory and statistics. Entropy measures how much information, on average, a single token carries. When tokens are more unpredictable, the entropy is higher, and you therefore need more bits to represent each token without loss. Imagine a language that labels positions in a square using only 2 tokens. Each token only tells you whether the position is upper or lower, so there are exactly 2 possibilities. With 2 equally likely choices, you need 1 bit to represent them. So the entropy of this language is 1 bit. Focus on the 2 adjacent squares and the numbers inside them. Notice how they're positioned and whether one appears highlighted or prioritized. That spatial relationship often signals comparison or sequence. Keep the numeric values and grouping in mind. We'll refer back to them when explaining the concept they illustrate. This figure compares 2 ways to describe positions inside a square. The left language uses simpler, lower information tokens, while the right language's tokens encode more information but require more bits to represent. With 4 tokens, you can mark 4 distinct positions: upper left, upper right, lower left, and lower right. Encoding 4 possible values requires log 2, 4 equals 2 bits, so the language's entropy is 2. That means each token carries more information than in a 2-token language, but it also needs more bits to represent. Entropy quantifies unpredictability. Lower entropy means tokens are easier to predict and each token carries less new information. For example, a language with only 2 tokens is more predictable than one with 4 because you choose from fewer options. If you could perfectly predict the next token, it would carry no new information at all. In this section, we'll define cross-entropy, the standard loss for classification that compares predicted probability distributions to true labels. We'll build intuition for why lower cross-entropy means predictions are closer to the correct distribution. When we train a language model, we want it to capture the distribution of the training data by predicting what comes next. Cross-entropy is the standard metric for this. It tells us, on average, how surprised a model is by the next token. Lower cross-entropy means better predictions and a closer match to the data. The cross-entropy we measure on the training set comes from 2 sources: the model's probabilistic fit to the true conditional distribution, and the intrinsic unpredictability in the data, irreducible label noise, or Bayes uncertainty. Even a perfectly fitted model cannot drive cross-entropy below the data's conditional entropy, so lowering cross-entropy reflects improved probabilistic predictions beyond the irreducible noise. This is the first step. We'll introduce the main idea and set up the problem, so everything that follows is clear. Pay attention to the goal and any assumptions we make here. We quantify how predictable the training data are using entropy, a statistical measure of uncertainty in the data distribution. Lower entropy means samples are more predictable, easier to compress or learn, while higher entropy indicates more randomness and typically requires greater model capacity. Begin by reading the whole problem carefully. Identify what is given, what is being asked, and underline key quantities or constraints before you start solving. A trained language model only approximates the empirical distribution of its training data, so its predicted probabilities won't match the true data frequencies exactly. Causes include the training objective, e.g., maximum likelihood, limited model capacity, pre-processing and tokenization, optimization noise, and the sampling or decoding method used at generation time. These shifts change properties like diversity, rare event frequency, and sometimes factual accuracy in generated text. Entropy and cross-entropy are both written with the symbol H, which can be confusing at first. We use P to mean the true distribution of the training data and Q for the distribution learned by the model. With that notation, we could directly compare the true uncertainty H, P, to the cross-entropy H, P, Q. This quantity measures the average uncertainty or surprise in the data distribution P and equals the minimal expected log loss, or bits per sample, achievable. It's the baseline target for models. Cross-entropy reaches H, P, only when the model exactly matches P. Otherwise, cross-entropy exceeds it by the KL divergence. The Kuhlback Leibler divergence gives a single number measure of how much the distribution Q differs from a reference distribution P. It's asymmetric and commonly used in statistics and machine learning to quantify information loss when Q is used to approximate P. This short paragraph states the central idea and why it matters. I'll highlight the core point now and move technical details to the next sections so you can follow the flow without getting lost. This identity breaks the model's cross-entropy into two parts. The intrinsic entropy of the data, H, P, plus the KL divergence between the true distribution and the model, D_KL, PQ. Because the KL term is always non-negative, the cross-entropy is at least the data entropy and equals it only when a model matches the data exactly. Cross-entropy usually depends on which distribution is used to average the log probabilities. H, P, Q averages log Q under P, while H, Q, P averages log P under Q, so they generally differ. They only match when P equals Q. We train language models by minimizing cross-entropy to the training distribution. If the model matches that distribution exactly, its cross-entropy equals the true entropy of the data, so the KL divergence KL, QP, is 0. In other words, cross-entropy is the model's estimate of the training data's entropy and its goodness of fit. In this section, we'll define bits per character and bits per byte and explain how they measure information in text and binary data. These concepts let us compare encoding efficiency and estimate storage or transmission costs. Entropy and cross-entropy are measured in bits, which count the average number of binary decisions needed to specify an outcome. If a model's cross-entropy is 6 bits, it will need on average 6 bits to represent each token, equivalent to about 64 equally likely possibilities per token. This number is the information theoretic cost of encoding tokens under that model. Different models tokenize text differently. Some use words, others use characters, so a bits per token number isn't comparable across models. To compare across tokenizations, we use bits per character, BPC divide bits per token by the average characters per token. For example, 6 bits / token with 2 characters / token gives BPC equals 6 divided by 2 is equal to 3. Different character encodings make BPC hard to compare. ASCII uses 7 bits per character, while UTF-8 can use 8 to 32 bits. BPB, bits per byte, rescales BPC to the original byte granularity by dividing BPC by bits per character divided by 8. For example, If BPC equals 3 and each character is 7 bits, 7/8 of a byte, then BPB equals 3 divided by 7/8 equals 3.43 bits per original byte. Bits per byte, BPB, is a cross-entropy measure that predicts how well a language model can compress text. With BPB equals 3.43, the model uses 3.43 bits on average to represent each original 8-bit byte, so the text could be compressed to about 3.43/8 is almost equal to 42.9% of its original size, i.e., less than half. Remember, this is an information theoretic limit. Real compressors may achieve different results in practice. We'll introduce Perplexity, a standard measure of how well a probabilistic model predicts a set of data. I'll give the intuition, the formula, and how to interpret higher versus lower perplexity. Perplexity, often written PPL, is the exponential of entropy or of cross-entropy when we evaluate a model against the true distribution. Practically, it equals the exponential of the average negative log probability the model assigns, and it represents the effective number of equally likely choices the model is predicting. Lower perplexity means the model is less surprised and generally better. This defines perplexity as 2 raised to the Shannon entropy h, p, where h is measured in bits. Intuitively, perplexity is the effective number of equally likely choices the distribution represents. Each extra bit of entropy doubles the perplexity. Perplexity quantifies how well the learned distribution Q predicts the dataset. Take the average negative log probability assigned by Q to the tokens, then exponentiate. Practically, perplexity is the model's effective number of choices per token. Lower values mean the model is more certain and fits the data better. This defines perplexity, PPL, from cross-entropy. PPL equals 2 raised to the cross-entropy h, PQ. Because h, p, q is measured in bits per token, 2 caret h, p, q gives the effective average branching factor, the number of equally likely choices the model behaves as if it had. Perplexity measures how uncertain a model is when predicting the next token. A higher perplexity means the model treats more tokens as plausible options, so prediction is harder and less confident. With 4 distinct position tokens encoded perfectly, the model's average cross-entropy is 2 bits because log 2, 4, equals 2. Perplexity is defined as 2 caret cross-entropy, so here 2 squared equals 4, matching the 4 equally likely position choices the model must pick from. We use bits as the unit for entropy and cross-entropy because 1 bit represents a binary choice, 2 equally likely outcomes. That is why perplexity uses base 2. It converts average log probabilities into the equivalent number of choices per token. Popular ML frameworks like TensorFlow and PyTorch compute cross-entropy with natural logarithms, so the unit is nats, logarithms base e. When entropy is measured in nats, perplexity is e to the entropy, written exp, entropy. If you instead measure entropy in bits, perplexity would be 2 caret entropy. PPL, P, Q is perplexity, and H, P, Q is the cross-entropy between the true distribution P and the model Q. Exponentiating the cross-entropy turns the average log loss into an intuitive effective number of choices per token. Lower perplexity means the model's predictions are closer to the true distribution. Because bits and nats use different logarithm bases, mixing them changes the numeric values you report. Many people end up quoting perplexity when they meant cross-entropy. Remember that perplexity equals exp, cross-entropy, so unit confusion can make model comparisons misleading. In this section, we'll define what perplexity measures for a language model and how to read its values. Then we'll cover practical situations where perplexity is useful and where it can be misleading, such as model comparison, dataset evaluation, and spotting overfitting. Perplexity, cross-entropy, bits per character, and bits per byte are all ways to measure how well a language model predicts the next token. I'll use perplexity as the default metric in this book, When a model is more uncertain about what comes next, perplexity increases. There's no single good perplexity value. It depends on the dataset, tokenization, and exactly how perplexity is computed, for example, the model's available context. In practice, lower perplexity usually means better next token predictions, but you must compare values only when the data and computation method are the same. When data has more structure, consistent formats, regular patterns, or constrained vocabulary, a model is less surprised on average. That reduced surprise is lower expected perplexity, which means the model's predictions are more confident and easier to learn. Structured formats like HTML enforce clear patterns and constraints. If a model sees an opening tag, the corresponding closing tag becomes very likely. So the model's uncertainty, perplexity, on HTML is typically lower than on unconstrained everyday text. When a model must pick from more possible tokens, its uncertainty, measured by perplexity, usually grows. Probability mass gets spread thinner across more choices, so the average surprise for the next token increases if everything else stays the same. When a model has more possible next tokens to choose from, its uncertainty increases and perplexity goes up. For example, predicting text from War and Peace is usually harder than a children's book, and predicting whole words is harder than predicting characters because the word vocabulary is much larger than the character set. Seeing more prior tokens lets the model condition its prediction on more information, so its predicted probability distribution becomes sharper and perplexity falls. This reduces uncertainty in next token prediction, though additional context yields diminishing returns once relevant information is already included. When a model sees more prior tokens, its uncertainty about the next token decreases. Shannon measured this effect in 1951 by evaluating cross-entropy using up to 10 previous tokens. Modern models compute perplexity conditioned on hundreds to thousands, or more, of tokens, limited only by the model's maximum context length. A perplexity around 3 means the model, on average, has about a 1 in 3 chance of predicting the next token correctly. That's striking because real model vocabularies contain tens to hundreds of thousands of tokens, so random guessing would be far, far worse. Perplexity is a measure of the model's uncertainty. Lower values indicate much stronger predictive power. Perplexity is more than a training statistic. It's a practical proxy for a model's capabilities. If a model is poor at predicting the next token, it will often perform poorly on real tasks. GPT-2 showed larger models have lower perplexity, but many firms have stopped publishing these numbers. This table summarizes evaluation across many datasets. As GPT-2 grows from 117M to 1.54B parameters, perplexity-like metrics, PPL, BPB, BPC, fall, and accuracy scores rise. Lower perplexity means the model assigns higher probability to the correct next token, and the consistent trend across Lambda, CBT, Wikitext, PTB, and others shows clear benefit from scale. Warning: important safety and correctness caveats follow. Read them carefully and don't skip them, because these points affect how you apply the rest of the lesson. Perplexity can be a misleading evaluation after post-training, like SFT or RLHF, because those methods teach the model to complete tasks, not necessarily to predict next tokens. As task performance improves, next token likelihoods can get worse, and measured perplexity often increases. This is sometimes called an entropy collapse. Quantization, which reduces numerical precision, can also change perplexity in unexpected ways. Perplexity measures how surprised a model is by a piece of text. Lower perplexity means the model predicts the text more easily. Text the model has seen during training typically produce very low perplexity, so unexpectedly low scores can reveal that a benchmark or example was included in the training set. Data contamination. You can also use this signal for deduplication. Only add new data whose perplexity under the current model is sufficiently high. Perplexity quantifies how surprising a piece of text is to a language model. The less predictable the words, the higher the perplexity. That means odd or semantically strange sentences, like "my dog teaches quantum physics," and nonsensical strings like "home cat go, I," produce large perplexity, so this metric can help detect abnormal or unexpected text. Perplexity and related metrics give an indirect measure of a language model's ability, but they're only a proxy for real application performance. In the rest of this chapter, we'll shift to evaluating models directly on downstream tasks and learn how to measure those task-specific outcomes. In this section, we'll define what perplexity measures and why it's a useful evaluation metric for language models. Then I'll outline the practical steps to compute perplexity from a model's token probabilities, including common pitfalls to watch for. Perplexity quantifies how difficult it is for a Model X to predict a specific token sequence. Formally, it's derived from the model's probabilities for each token, essentially the exponential of the average negative log probability. So a lower perplexity means the model assigns higher probability and finds the sequence easier to predict. We rewrite the inverse nth root of the joint probability as the nth root of the product of inverse conditional probabilities, because the joint factorizes as p x1 xn equals pi underscore I p x underscore I x underscore O. This shows the expression is the geometric mean of the inverse conditionals, a per symbol measure closely related to average surprise or perplexity. This denotes the conditional probability the model X assigns to the next token X underscore I, given all earlier tokens X underscore 1 through X underscore n. In autoregressive models, we use these stepwise conditional probabilities to compute the probability of an entire sequence. To compute perplexity, you need the model's probabilities or log probabilities for each next token. Many commercial models don't provide log probs, so you can't always calculate perplexity directly. See Chapter 2 for more on which models expose this data. In this section, we'll learn how to compute expressions and limits exactly, producing closed-form answers rather than numerical approximations. I'll introduce core techniques, algebraic simplification, substitution, and common identities that let us obtain precise evaluations. Some evaluations are exact and unambiguous. For example, a multiple-choice question has a single correct answer, so a wrong choice is clearly wrong. Other tasks, like grading an essay, are subjective. Different graders, or the same grader at different times, can assign different scores. Clear rubrics can reduce subjectivity, but they don't eliminate it. AI used as a judge is also subjective. The chosen judge model and the prompt can change the evaluation outcome. We'll cover two evaluation methods that give precise scores. Functional correctness, which verifies whether a response fulfills the required task, and similarity measurements that compare outputs to reference answers. This section concentrates on open-ended text generation. Closed-ended tasks like classification are important, but are already well understood and often handled separately in system pipelines. In this section, we define functional correctness and explain why it's the key property when verifying programs. We'll outline how to state a program's specification and the typical structure of a correctness proof. Functional correctness measures whether a system actually performs the task you asked it to do. For example, if you ask a model to build a website, verify the site meets your specifications. If you ask it to make a restaurant reservation, verify the reservation was successfully completed. Functional correctness is the fundamental metric. It asks whether your application actually performs the tasks it was designed to do. In practice, this is difficult to measure automatically. It needs well-designed tests, real user checks, and human judgment to interpret results. When a model writes code, we can often verify correctness automatically by executing it. First, make sure the code runs in a Python interpreter. If it doesn't run, it isn't valid code. Then test it on representative inputs. For example, GCD 1520 must return 5, otherwise the function is wrong. Before AI-assisted coding, verifying functional correctness was standard practice. Engineers run unit tests that execute code in many scenarios to ensure expected outputs. This is exactly how coding platforms like LeetCode and HackerRank validate submitted solutions. Many popular benchmarks for code generation and text-to-SQL evaluate models by functional correctness, meaning the generated program or SQL must produce the correct results on test cases. Examples are Human Eval and MBPP for general code generation, and Spider, BRDSQL, and WikiSQL for text-to-SQL. A benchmark problem is evaluated with a set of test cases. Each test case describes a scenario to run and the exact expected output the code must produce. Human Eval, for example, lists such input-output examples that an automated checker runs against your solution. This block defines has underscore for elements, numbers, threshold, which should tell us whether any two numbers in the list are closer than the given threshold. The docstring includes small examples, and the check function lists assert-based test cases we need to satisfy. A common efficient approach is to sort the list and then scan adjacent pairs, since only neighbors can be closer than the threshold after sorting. For each problem, we generate k code samples. A problem is counted as solved if any one of those k samples passes all the problem's tests, and pass at k is the fraction of problems solved across the whole set. For example, if there are 10 problems and with k equals 3 we solve 5 of them, pass at 3 equals 50%. Because more samples give more chances to find a passing solution, expected scores increase with k. So pass at 1 less than or equal to pass at 3 less than or equal to pass at 10. When a task has a clear, measurable objective, you can automatically judge how well an agent performs. For example, a Tetris bot is evaluated by its score, and a workload scheduler can be measured by the energy it saves. In these cases, we use functional correctness, a numeric metric, to compare and optimize solutions. Now we'll learn how to compare model outputs to reference data using common similarity metrics. I'll introduce metrics like BLEU, ROUGE, and cosine similarity, and explain when each one is appropriate and what their scores mean. When you can't automatically test correctness, a common approach is to compare model outputs to reference data, known correct answers, or human examples. For example, to evaluate a French-English translation, you compare the model's English sentence to the correct English translation, using automatic metrics or human judgment. Each example pairs an input with one or more reference responses. These references are the canonical or ground truth outputs. Metrics that evaluate model outputs by comparing them to these references are called reference-based. Metrics that don't rely on references are reference-free. Evaluation that compares model outputs to reference data is limited by how much reference data we can produce and how fast. Human-written references are treated as the gold standard, but are expensive and slow to create. Many teams now use AI to generate references and then perform lighter human review, which cuts overall labor but doesn't remove the need for verification. We judge a generated answer as better when it's more similar to one or more reference responses. There are 4 broad ways to measure similarity between open-ended texts, each focusing on different signals: surface overlap, semantic closeness, edit-based difference, or model-derived scores. Begin by stating the problem or goal you want to solve. A clear, specific objective focuses your approach and makes the next steps easier to choose. Tell the evaluator to compare the 2 texts and decide whether they are the same. Specify whether you mean an exact string match or a semantic equivalence, and give brief criteria or examples so judgments are consistent. Start by reading the problem carefully and identify exactly what is being asked. Note the given information, any constraints, and the desired form of the answer so you can plan a correct approach. An exact match means the model's output is identical to one of the reference responses, character for character. It's a strict metric. Only perfect copies get credit, so small differences in wording, punctuation, or spacing count as failures. Begin by naming the first item or goal clearly. Then break it into a single, specific task and decide the immediate next action to take. Lexical similarity measures how much a generated response matches reference responses at the surface level. For example, overlapping words or n-grams. It helps detect literal copying or word-level fidelity, but can miss cases where different wording preserves the same meaning. Start by stating the problem clearly, what is given and what you need to find. Also note any assumptions or units so the rest of the solution stays consistent. Semantic similarity measures how close a generated response is to reference responses in meaning, not just in shared words. We use it to check whether two texts convey the same idea, typically computed with embeddings, paraphrase models, or human judgments. When we compare two responses, the judgments can come from human evaluators or from automated AI evaluators. AI evaluators are becoming more common because they scale and can be systematically tuned. We'll focus on how they work and when to use them in the next section. We commonly use three hand-designed metrics: exact match, lexical similarity, and semantic similarity. Exact match is binary. Either the output equals the reference or it doesn't, while lexical and semantic measures produce graded scores, for example 0 to 1 or -1 to 1, that capture partial agreement. Even though AI-as-Judge methods are flexible, industry workflows still rely on these hand-designed metrics for their precise, interpretable signals. This brief note flags an important caveat you'll need for the next section. Keep it in mind as we work through the examples that follow. Similarity measurements let us quantify how close a model's output is to a reference, often by comparing embeddings or token-level scores. They also support many other tasks such as semantic search, clustering, deduplication, monitoring, and personalization. We'll list those next. Retrieval pulls the most relevant documents or data items from a large collection, often using indexes or vector embeddings to match meaning. Search is the broader process of locating and ranking information, using keywords, filters, or relevant signals. And retrieval systems are the backend that power user-facing search and features like retrieval-augmented generation for LLMs. We retrieve items that resemble a given query by comparing representations, usually vector embeddings, for the query and each candidate. The system ranks candidates by a similarity metric, for example cosine, and returns the nearest neighbors, which powers recommendations and semantic search. Ranking means arranging items in order according to a criterion or numeric score, so we can compare and select the best entries. This appears in search, recommendations, and competitions. Practical issues include handling ties and choosing a stable, explainable ordering. For each item, we compute a similarity score with the query, then sort the items by that score to put the most relevant ones first. This is the basic mechanism behind search and recommendations. Similarity can be computed from embeddings, feature vectors, or simpler text overlap measures, depending on the application. Clustering is an unsupervised task that partitions data into groups or clusters so that items within a cluster are more similar to each other than to items in other clusters. We use clustering for exploratory analysis, anomaly detection, and pre-processing. Common methods include k-means, hierarchical clustering, and DISCAN. Clustering groups data points so that members of the same cluster are more similar to each other than to members of other clusters. Similarity is defined by a metric, like Euclidean distance or cosine similarity, and that choice shapes the clusters you get. Anomaly detection finds data points that deviate from expected patterns. It's used for fraud detection, fault monitoring, and system health by modeling normal behavior and flagging deviations. Methods can be supervised, unsupervised, or semi-supervised. This task is about finding items that stand out because they are unlike the others. We typically compute pairwise similarity or distances, then flag items with consistently low similarity or high distance, small cluster membership, or unusual feature values. In short, the likely outliers. Data deduplication means finding and removing duplicate records so each real-world entity appears only once. Approaches include exact methods, hashing/fingerprints, and fuzzy/record linkage techniques that handle typos and variants. Deduplication saves storage, prevents double counting, and improves data quality for analysis. If items are nearly identical, drop the extras to reduce redundancy and improve coverage. Identify candidates with a similarity metric or clustering. Then apply a threshold or a quick manual check to keep the most representative examples. The methods we introduce here won't be one-offs. You'll encounter and reuse them in later chapters and examples. Pay attention to both why they work and how they're applied, because later sections build on these ideas. We'll define what an exact match means and why it matters. Next, I'll give the formal idea and a short example to make it concrete. An exact match means the generated response is identical to one of the reference answers. This measure is appropriate for tasks that expect short, definitive outputs, simple math, common knowledge facts, or trivia, where only one precise string is considered correct. This paragraph distills the central idea you should remember. Identify the mechanism, its inputs and outputs, and the single key assumption that makes it work. As you study examples, map each step back to this core idea so you avoid getting lost in incidental details. This asks for the sum of 2 and 3. Adding them gives 5, since 2 objects plus 3 objects equals 5 objects. This short paragraph pulls together the essential point you just saw and explains why it matters. Focus on the central concept, any cause and effect, and the practical implication for what you'll do next. The first woman to win a Nobel Prize was Marie Curie. She received the 1903 Nobel Prize in Physics, shared, and later won the 1911 Nobel Prize in Chemistry, becoming the first person awarded Nobels in 2 different sciences. This paragraph is intentionally left blank as a placeholder. It marks a brief pause or separation before the next concept, and content may be added here later when we expand this section. This is a typical user request to a banking assistant asking for their current balance. To answer safely and accurately, the system must authenticate the user, retrieve the latest ledger and available balances, and consider any pending transactions. State the main idea clearly in one sentence, then add a brief example or one supporting detail if needed. This helps the learner grasp the concept quickly and leaves room for deeper examples or exercises later. This analogy asks which city relates to England the same way Paris relates to France. Because Paris is France's capital, the corresponding city is London, the capital of England. One tolerant matching rule treats any output that contains the reference response as a match. For example, if the question is, what's 2 plus 3, and the reference is 5, then the answer is 5, or 2 plus 3 is 5. Both count as matches despite different formatting. Consider the question, what year was Anne Frank born? The factual answer is 1929. She was born June 12, 1929. If a model replies September 12, 1929, it contains the correct year, yet the response is factually incorrect, showing that partial matches, like spotting the year, can let wrong answers pass. Exact match scoring is brittle for tasks like translation because many different outputs can be correct. For example, comment CAVA can be rendered as how are you doing, or how is it going? If the reference set omits a valid phrasing, the model gets penalized. As inputs grow longer and more complex, exhaustive references are impossible, so lexical or semantic similarity metrics give a fair evaluation. Now we'll look at lexical similarity, how much 2 languages or texts share in vocabulary. I'll explain common ways to measure this overlap and why it matters for transfer and understanding. Lexical similarity measures how much 2 texts share in common by comparing their tokens. First, tokenize each text, words, subwords, or n-grams. Then compute overlap, for example using shared token counts, the jacket index on token sets, or cosine similarity on token count vectors. A simple lexical similarity measure just counts how many tokens 2 texts have in common. For the reference, my cats scare the mice, we compare which words appear in both the reference and a generated response. The overlap size is the score. This ignores order and meaning, so it's a blunt metric. Show just one clear idea on screen and avoid long sentences. Use your narration to give the full explanation, examples, and nuance so viewers can follow without reading too much. This short sentence demonstrates possession and agreement. My shows possession. Cats is a plural subject, so the verb stays in its base form, eat, in the present simple. The mice is a definite plural object, so the whole sentence reads as a habitual or general statement about what the cats do. This dash marks a placeholder where content will be added shortly. It signals that the idea or example for this spot is intentionally left out for now and will be filled in next. This sentence is a sweeping generalization. It asserts constant conflict between cats and mice. In reality, their interactions vary, sometimes predation, sometimes avoidance, and often no encounter at all. So all the time is an overstatement. Here we treat each token as a word and compute similarity by counting overlapping words. Response A shares 4 of 5 words with the reference, 80%, while response B shares 3 of 5, 60%. Because it has the higher overlap percentage, it's judged more similar. We measure lexical similarity by counting the minimum edits needed to turn one string into another. That number is the edit distance. The usual edit operations are insertions, deletions, and substitutions. A smaller distance means the texts are more similar. Begin by reading the problem carefully. Note what information is given, what you're asked to find, and any constraints or units. Pinpointing these elements narrows possible approaches and prevents mistakes later. This shows a deletion. The underscores mark remove characters. Removing the middle letters from B__add compacts the remaining letters to produce bad. This marks the first item in our sequence. In the next lines, I'll explain the first point clearly and show what matters about it. Insertion means adding a character into a string. For example, inserting underscore after the in bad produces v. The string is one character longer, and this models an added symbol in alignment or edit distance comparisons. Begin by writing down every quantity or condition the problem gives and clearly state what you must find. If helpful, sketch a quick diagram and assign symbols to unknowns. This makes the solution steps much easier to plan. This shows a substitution. We replace the middle letter with E, turning bad into bed. A one-letter change like this changes both the pronunciation and the meaning of the word. Some fuzzy match systems treat a transposition, swapping 2 adjacent letters, as a single edit operation. For example, underscore can be counted as one transposition. Other systems instead model that swap as a deletion plus an insertion, 2 edits, which changes the computed edit distance and therefore the match score. This illustrates edit distance as a similarity measure. Converting bad to bar requires 1 edit, but converting bad to cache requires 3, so bad is considered closer to barred. N-gram similarity compares sequences of tokens, n-grams, between a reference and a generated response. For example, my cats scare the mice yields these big grams. My cats scare the mice. The score is the percentage of reference n-grams that also appear in the generated text. You can vary n, 1 for unigrams, 2 for bigrams, to focus on different levels of sequence matching. These metrics measure lexical overlap between a system output and reference text, but they differ in exactly how overlap is computed. For example, n-gram matches, edit distance, or weighted consensus. They were widely used for translation and captioning before large foundation models became common. Today, fewer benchmarks rely only on lexical scores, though Walmart, Coco Captions, and GMB2 still use them. This evaluation approach needs a comprehensive set of reference responses. If valid answer variants aren't in the reference set, a correct model output can receive a low similarity score, as happened with BLEU on some image captioning examples, where correct captions were penalized because matching references were missing. The Walmart 2023 metrics shared task organizers found many incorrect or low-quality reference translations in their evaluation data. Those flawed references weaken reference-based evaluations and help explain why reference-free metrics often correlated with human judgments as well as, or better than, Reference-based metrics, Freitag et al., 2023. High lexical similarity scores like BLEU don't always indicate a correct or working answer. For example, on the human eval code benchmark, OpenAI found BLEU scores were similar for correct and incorrect solutions, so optimizing BLEU doesn't guarantee functional correctness. Chen et al., 2021. This screenshot shows a computer application window. Pay attention to the overall layout and the placement of key UI elements. Look for the title bar, menus, or toolbars, and any highlighted text or icons that signal important actions or messages. This figure illustrates a case where Fuyu generated a correct option but received a low score because the reference captions were limited. We'll look briefly at how evaluation against narrow references can penalize valid outputs. In this section, we'll define semantic similarity and why it matters for NLP tasks. We'll focus on practical, embedding-based ways to measure meaning, like cosine similarity and nearest neighbor comparisons. Lexical similarity measures surface overlap in words or characters, not whether two texts share the same meaning. For example, "What's up?" and "How are you?" look different lexically but are close in meaning. Conversely, nearly identical texts can mean very different things. Compare "Let's eat grandma" with "Let's eat grandma." Semantic similarity measures how close two texts are in meaning by first converting each text into a numeric vector called an embedding. For example, the sentence "the cat sits on a mat" might be represented as 0.11, 0.02, 0.54. Comparing these vectors, for example, with cosine similarity, tells us how semantically alike the texts are, which is why it's also called embedding similarity. Embeddings convert text into vectors, so we can compare meanings numerically. A common metric is cosine similarity, which ranges from -1 for opposite vectors through 0 for unrelated to 1 for identical vectors. For now, assume you can produce embeddings and use their cosine scores to judge how similar two texts are. Here I use text examples, but the method is the same for images or audio. Convert each item into an embedding vector and compare distances or similarities. When applied to text, this measurement is often called semantic textual similarity. This section highlights important warnings and limitations you must keep in mind. Pay close attention to potential pitfalls and safety considerations as we proceed. The similarity value between two embeddings is computed exactly. Given the vectors, the math yields a precise score. However, which scores count as similar depends on the embedding model and your application, so interpretation is inherently subjective. Here, A is the embedding of the generated response, and B is the embedding of a reference. We compute cosine similarity by taking the dot product AB and dividing by the product of their Euclidean norms, AB. This yields a score between -1 and 1 that measures how aligned the two embeddings are. The dot product AB is a scalar equal to AB cos, so it measures how much it points in B's direction. We use it to compute projections and to test orthogonality. If A and B equals 0, the vectors are perpendicular. This is the L2 Euclidean norm. It gives the length or magnitude of vector A. Computing it by squaring components, summing, and taking a square root is essential for tasks like normalization and measuring distances between vectors. Both are metrics for semantic textual similarity that compare text meaning using embeddings instead of exact word matches. BERTScore generates embeddings with BERT and compares token-level similarity. MoverScore combines multiple embedding methods to capture complementary semantic signals across words and phrases. Semantic similarity lets us compare meanings without an exhaustive set of reference responses, because it uses vector embeddings rather than exact word overlap. Its reliability hinges on the embedding model. Poor embeddings can give low similarity scores for sentences that actually mean the same thing. Also note that generating high-quality embeddings can require non-trivial compute and time. An embedding converts text or other data into a numeric vector so that semantically similar items end up close together in that vector space. This idea is the foundation for many techniques we'll see later. For example, vector search in Chapter 6 and data deduplication in Chapter 8. In this section, we'll define what embeddings are and why they're useful in machine learning and search. I'll give the intuition behind representing items as vectors and preview the common applications we'll study next. Because models only work with numbers, we convert inputs into vectors called embeddings. An embedding is a compact numeric representation that preserves semantic relationships, so similar inputs end up near each other in vector space. These vectors let the model compare and manipulate meaning mathematically. An embedding represents text as a list of numbers, so computers can measure similarity in meaning. The three-number vector shown is just an illustration. Real embeddings are much larger, typically hundreds to thousands of dimensions, commonly on the order of 100 to 10,000. Some models are trained specifically to produce embeddings, compact numeric vectors that represent text or images. Open-source examples include BERT, CLIP, and the sentence transformers family. Many companies also provide proprietary embedding APIs. Table 3-do lists typical embedding dimensionalities for popular models. Different models use different embedding dimensionalities. BERT offers 768 base and 1024 large. CLIP uses 512 for both image and text. OpenAI provides 1536 and 3072 variants. Cohere has 1024 and 384 options. Higher dimensions can represent finer detail, but increase storage, compute, and the cost of nearest neighbor search. Most ML models convert inputs into vector embeddings. Transformer models expose an embedding layer and intermediate activations you can read out. If you have access to those layers, you can extract embeddings, but models trained specifically for embedding tasks typically produce higher quality vectors for semantic search and similarity. An embedding like 0.11, 0.02, 0.54 won't look like the sentence it came from, and that's okay. Embeddings are numeric summaries. We verify they capture meaning by checking that similar sentences produce nearby vectors, via cosine similarity or nearest neighbors, by inspecting clusters, and by measuring performance on downstream tasks. We evaluate embeddings by whether semantically similar sentences map to nearby vectors, usually measured with cosine similarity. For instance, the cat sits on a mat should be closer to the dog plays on the grass than to AI research is super fun. This property is what makes embeddings useful for search, clustering, and semantic comparisons. A practical way to judge embedding quality is to measure how useful they are for the tasks you care about. For example, classification, topic modeling, recommendation, or retrieval augmented generation. Benchmarks, such as MTB, run many of these tasks and let you compare models based on real downstream performance. I often use text examples, but embeddings can represent any data type. Companies like Criteo and Covio embed products, and Pinterest embeds images, graphs, queries, and even users to power search, recommendations, and personalization. Researchers create shared embedding spaces so different data types can be compared and used together. CLIP showed how to align text and images in one space. ULIP extended this to include 3D point clouds alongside text and images. ImageBind goes further, learning a single embedding across 6 modalities, for example, text, images, and audio. These unified representations enable cross-modal retrieval, zero-shot transfer, and multi-sensor reasoning. CLIP trains on image-text pairs. The text is usually a caption or comment for the image. A text encoder and an image encoder convert each input into embeddings. Then both embeddings are projected into a shared embedding space where the model is trained to pull matching image, text pairs close together, and push mismatches apart. This diagram shows the main parts of a computer and how they connect: CPU, processor, memory, storage, and input-output. Pay attention to the lines between components. Those represent the data and control pathways that let the parts communicate. This figure summarizes CLIP's design: separate encoders for images and text trained together so their embeddings align. We'll use this diagram to step through the image branch, the text branch, and the contrastive training objective that ties them together. A multimodal embedding space maps different data types, like images and text, into one shared vector space. There, an image of a man fishing will sit close to the text of fisherman and far from unrelated captions like fashion show. This lets you compare modalities directly and perform tasks, such as text-based image search, by retrieving images nearest a text query. We'll explore what it means to deploy AI systems in judging roles, from fully automated decisions to tools that assist human judges. I'll highlight potential benefits, key limitations, and the ethical and legal trade-offs to watch for. Scoring open-ended responses is difficult. So many teams rely on human evaluation. That raises the question, can AI automate evaluation itself by using one model to judge another? This idea, often called AI as a judge or LLM-as-a-Judge, refers to an AI model used specifically to evaluate other models. Using AI to automate evaluation has been discussed for years, but it only became practical once models like GPT-3 arrived around 2020. Since then, using AI as a judge has become widespread in production evaluations. For example, LangChain reported that 58% of evaluations on their platform in 2023 were done by AI judges, and it remains an active research area. Let's examine why people are considering AI to make or assist judicial decisions. We'll cover the potential benefits, the new risks it introduces, and the trade-offs that determine where AI might be appropriate. AI judges can score outputs much faster and cheaper than human evaluators. Many operate without reference answers, which makes them practical for production settings where no reference data exists. You can ask AI models to evaluate outputs along many dimensions: correctness, repetitiveness, toxicity, wholesomeness, hallucinations, and so on. Models reflect aggregated human patterns, so with the right prompt and model you can get broadly useful, representative judgments, but you should not assume every judgment is correct. Recent studies show AI evaluators closely track human judgments. Zhang et al., 2023, found GPT-4 agreed with humans 85% on the MT bench, higher than the 81% human agreement, and Du Bois et al. Reported alpaca eval scores correlate about 0.98 with a human-rated leaderboard, suggesting AI judges can serve as reliable proxies for many evaluation tasks. Modern models can do more than assign a score. They can also explain why they made that decision. Those explanations are useful for auditing evaluations. You can inspect the model's rationale to find mistakes, biases, or surprising criteria. See Figure 3.7 for an example. AI judgments are flexible, so they can be used across many evaluation tasks and sometimes are the only practical automated option. Even if they fall short of human performance, their speed and scalability often make them good enough to guide development and help get a project off the ground. This image shows a screenshot of a paper with an automatically generated description. Notice the overall layout, title area, body text, and any figures or captions, and how the generated caption is generic and may miss important specifics like author names, figure details, or context. This figure shows that AI evaluators can do more than assign a numeric score. They can also produce explanations that justify their decisions. We'll examine how scoring and explanation mechanisms work together and what that means for transparency. In this section, we'll cover when and how to use AI as a decision maker, what constraints to impose, and how to verify its rulings. We'll focus on practical safeguards and evaluation strategies so you can rely on AI outputs responsibly. You can ask an AI to judge a response in 3 basic ways: evaluate the response on its own, compare it to a reference answer, or compare it to a different response. Each method has different strengths. Direct evaluation is simple but subjective. Reference comparison checks correctness or coverage, and pairwise comparison is great for preferences and fine-grained choices. Later, we'll look at short example prompts for each approach. Begin by reading the problem carefully. Identify what information is given, what you're asked to find, and any constraints or units. Restating the goal in your own words prevents missteps and guides your plan. Assess the answer using only the original question as context. Focus on correctness, completeness, relevance, and clarity. Does the response directly answer what's asked, avoid unsupported assumptions, and provide enough detail without introducing unrelated information? This is a short rater prompt that asks a reviewer to assign a numeric quality score from 1 to 5. Notice the explicit scale lines. 1 means very bad through 5 means very good, and the placeholders question and answer. The template expects you to replace those with the actual items and then return a single numeric score. Treat the rubric consistently. Map major failures to 1 to 2, partial or mixed quality to 3, and clear, accurate, well-explained answers to 4 to 5. Start by putting the problem into your own words and listing what is given and what you need to find. This quick restatement removes ambiguity and makes the first actionable step clear. Instead of relying on hand-designed similarity metrics, directly compare a generated response to a reference. Look for whether they convey the same facts, correctness, and intent, and mark any substantive differences. This treats equivalence as a practical judgment about content and meaning rather than an abstract score. This is a short evaluation prompt. It asks you to compare a generated answer with a reference answer and return either true or false. The placeholders, question, reference answer, and generated answer must be filled in before performing the comparison. The important constraint is to output exactly true or false as the final response. Begin by reading the problem carefully. Underline key words, write down the givens and the unknown, and, if it helps, sketch a quick diagram or restate the goal in your own words. We compare 2 generated responses to decide which a user would prefer. This produces preference data that can be used for post-training alignment, for selecting outputs at test time under compute limits, and for training or evaluating ranking models through comparative evaluation. This is a prompt template that asks a reviewer to pick the better of 2 candidate answers for a given question. The important parts are the placeholders. Question A, first answer, and B, second answer. And the final line, the better answer is, which expects a single token reply, either A or B. Note this is a text prompt, not executable code. Treat it as instructions for evaluation rather than a runnable program. An AI judge evaluates a model's output against whatever criteria you define. For example, you can check role consistency. Does this sound like Gandalf? Or ask for numeric judgments like, rate the product's trustworthiness from 1 to 5. Many tools also provide built-in judging criteria you can reuse or adapt. Many AI platforms supply built-in judge criteria to evaluate model outputs. Examples include groundedness, faithfulness, relevance, coherence, fluency, and safety flags such as harmfulness or misogyny. Different tools, Azure AI Studio, LangChain, MLflow, ROUGE, include different sets of criteria, and these built-in metrics will continue to change as the tools evolve. Relevant scores from different judges aren't standardized. Azure AI Studio can score the same result very differently than MLflow. Those differences stem from each judge's underlying model, prompt, and configuration. So treat scores comparatively and consider calibrating or using a single judge for consistent evaluations. Prompting an AI judge follows the same principles as any effective prompt. Be explicit about what you want judged and how. Provide a concise task description, clear evaluation criteria or rubric, representative examples, including edge cases, any constraints or assumptions, the exact output format you expect, and, when possible, calibration or reference answers so the judge can align its scoring. Begin by stating the problem clearly and fixing your notation. Identify any assumptions and what you intend to prove or compute so the following steps are unambiguous. The model's job here is to judge how well a generated answer matches the original question. That means checking whether the answer is on topic, directly addresses the question, and provides useful, relevant information. This mark denotes the first item in a sequence. Treat it as the label for the initial key idea or action we'll explain next. When evaluating a generated answer, your primary focus should be whether it contains sufficient information to address the question according to the ground truth. Be specific in the criteria you give. More detailed instructions lead to more consistent and accurate judgments of completeness and relevance. Start by reading the problem carefully. Identify what information is given, what you're asked to find, and any constraints or special conditions you must respect. The scoring system determines how responses are evaluated. Here we'll list the possible options you may encounter and then explain what each one means. This block contains only a dash and serves as a placeholder, so there is no explanatory prose here. We'll move on to the next section for the substantive material. Classification is the task of assigning each input to one of a fixed set of discrete labels. Common examples are binary labels like good versus bad or multi-class labels such as relevant, irrelevant, or neutral. Models learn these distinctions from labeled examples to support decisions and filtering. This brief paragraph states the main idea you need to keep in mind and why it matters. It highlights the core concept and any simple assumptions so you're ready for the details that follow. Discrete numerical values take a small set of numbers, like ratings 1 through 5. You can view this as classification because each possible number is its own class, but unlike arbitrary labels, the classes carry numeric and often ordinal meaning, which changes how we model them. Show only the essential phrase or claim on the canvas so viewers can read it at a glance. Use your spoken explanation to give the details, examples, and connections that make the idea useful and memorable. We represent similarity with a continuous number, commonly between 0 and 1, so we can show how close two items are instead of just yes/no. These scores let you rank results, choose thresholds, and treat similarity as a confidence-like measure. Quick tip: break complex tasks into small, verifiable steps and test as you go. This habit prevents large, hard-to-find bugs and keeps your progress visible. Language models generally excel at linguistic tasks, summarizing, classifying, and generating text, rather than precise numeric reasoning. Researchers also report that AI evaluators tend to be more reliable when asked to make categorical judgments, classification, than when asked to assign fine-grained numerical scores, which often require careful calibration. When we label data numerically, using discrete categories typically gives better model results than trying to predict a continuous value. Empirically, increasing the number of discrete bins often reduces annotator consistency and hurts performance, so wider ranges tend to worsen outcomes. For this reason, many scoring systems keep a compact scale, such as 1 to 5. Prompts that include examples tend to work better. If you use a 1 to 5 scoring system, show a sample response for each score, 1 through 5, and briefly explain why each response earned that score so raters understand criteria. This reduces ambiguity and improves consistency. See Chapter 5 for fuller prompting best practices. This excerpt shows how Azure AI Studio defines the relevance criterion. It states the task, the evaluation criteria, the scoring system, and a low-score example with an explanation. Part of the prompt was removed, but the visible portion illustrates how evaluators decide whether a response matches the user's intent and why an example scored poorly. This code-like instruction tells you to assign a relevance score from 1 to 5, comparing a generated answer to the question using the ground truth answer. Focus on whether the generated answer contains sufficient information to address the question. Contradictions should get a low score, 1 to 2. Partial or incomplete matches get mid-scores, and full agreement gets high scores. The sky example shows how a direct contradiction maps to a low score and should guide your reasoning. This figure illustrates an AI judge that reads a question plus a candidate answer and then scores how well the answer addresses the question. Automated judges speed up evaluation, but their accuracy depends on the rubric and how closely the model's judgments match human evaluators. This diagram highlights a central question and the relationships around it. Notice the central element, the question, the arrows that show information flow, and any labeled nodes that represent inputs or outputs. These visual cues turn an abstract question into a structured problem you can analyze. This figure presents an AI judge, a model that evaluates how well an answer responds to a question. We'll use it to see what criteria the judge applies and why that matters for improving responses. An AI judge isn't just the model weights, it's the whole system. The selected model, the prompt you give it, and the sampling settings, for example, temperature or top P. If you change the model, the prompt, or the sampling parameters, you effectively create a different judge with different behavior and scores. Now we'll examine why current AI systems are poorly suited to serve as impartial judges. We'll cover the key technical, ethical, and legal constraints that create real risks if we treat AI as an authority in disputes. Teams often resist AI as judge for a few practical reasons. It can feel tautological to have AI evaluate AI. Model outputs are probabilistic, so perceived as less reliable, and adding an AI evaluator introduces extra cost and latency. Because of these concerns, many treat AI judges as a fallback rather than the primary production evaluation method. Inconsistency means a set of statements or a model contains contradictions that cannot all be true together. In this section, we'll define inconsistency formally, look at quick examples, and outline simple ways to detect it. A trustworthy evaluation needs consistent results, but AI judges are inherently probabilistic. The same judge can produce different scores for the same input, depending on the prompt, and even on repeated runs with the same prompt. That variability makes results hard to reproduce and undermines confidence in the evaluation. Chapter 2 covers using sampling and prompt design to make an AI judge more consistent. Zhang et al. 2023 showed that adding evaluation examples raised GPT-4's consistency from 65% to 77.5%. But consistency can just mean repeating the same mistakes rather than being more accurate. Longer prompts also increase inference cost. In their experiment, adding examples roughly quadrupled GPT-4 spending. In this section, we'll define criteria ambiguity and why it matters. I will show how vague or inconsistent rules lead to different judgments and what we'll do next to clarify them. AI as judge metrics like faithfulness aren't standardized, so you can't directly compare scores across tools. For example, MLflow uses a 1 to 5 scale, ROUGE is binary, 0 or 1, and LLAMA-index expects yes/no. Treating these as equivalent can easily lead to misinterpretation or misuse. Evaluation tools often ship with very different default prompts, and those wording differences change what is actually scored. For example, MLflow's faithfulness instruction explicitly tells scorers to ignore the original input and judge only whether the provided output is factually consistent with the provided context, a framing that can produce systematically different scores than other tools. Score 1 means none of the statements in the output can be inferred from the provided context. This indicates unsupported information or hallucination, so the output is unreliable and should be marked incorrect or revised. Different tools and datasets use different label formats for judging faithfulness. For example, ROUGE expects 1 when a statement is verifiable from the context and 0 otherwise, while LLAMA-index asks for yes if any context supports the information and a no otherwise. Other evaluations use a 1 to 5 score range, so always note which convention you're using and map labels consistently. Raw scores from different faithfulness tools use different scales and meanings, so you can't compare them directly. Pick one tool and use it consistently, or calibrate/map each tool to a common scale, e.g., faithful/unfaithful, using a labeled validation set. Prefer the tool whose rubric matches your definition and validate on a small test set. You want a stable evaluation setup. Fixed metrics let you track how an application evolves over time. But keep in mind that AI judges are themselves software that can change, so shifts in evaluation may reflect changes in the judge as well as changes in the application. A jump from 90% to 92% doesn't prove your app's coherence improved unless the AI judges and their prompts were the same. Small differences, a changed judge prompt, a typo fix, or a more lenient evaluation prompt, can make scores look better even when the underlying behavior hasn't changed. When the application and the AI judge are managed by different teams, the judge team can change evaluators without telling the app team. That can make the application team see different evaluation results and incorrectly attribute them to changes in their code. Track judge versions and add clear metadata/communication so result shifts are traceable. Here's a concise, practical suggestion to help you apply the concept we just covered. Use this tip to avoid a common mistake and speed up your workflow. Always insist on seeing which model and the exact prompt an AI judge used before trusting its verdict. If either is hidden, you cannot audit for bias, prompt engineering tricks, or other evaluation failures. Evaluation approaches evolve gradually. As the field develops shared protocols and practical guardrails, automated AI judges will become more consistent and trustworthy. That growing standardization will improve the reliability of comparisons and safety assessments. Now we'll examine how higher costs and added latency affect systems. I'll point out common causes, how they impact performance and budgets, and what to monitor next. AI judges can run during experimentation to score and compare model outputs, and they can also operate in production as automatic filters. Many teams deploy them as guardrails that only surface responses the judge marks as acceptable, which helps reduce harm and maintain quality. If you use a powerful model like GPT-4 to both generate and evaluate responses, you multiply the number of model calls and therefore your API bill. For example, one generation call plus 3 separate evaluation prompts becomes 4 GPT-4 calls per example, about a 4 times cost increase. So consider cheaper evaluators, smaller models, or fewer evaluation criteria where appropriate. You can save money by using cheaper, weaker models as automatic judges and by spot checking only a subset of responses. Spot checking reduces cost, but can miss some failures. Increasing the sample size raises confidence and also raises cost. Finding the right trade-off between cost and confidence usually takes some trial and error. But even so, AI judges are far less expensive than hiring humans. Running an AI judge synchronously before returning a response reduces safety and quality risks, but increases end-to-end latency. For applications with strict latency budgets or real-time UX requirements, that extra delay can make inline judging impractical. In this section, we'll examine how AI systems can be biased when used for judging or decision-making, and why that matters. We'll outline common sources of bias and the practical consequences for fairness and trust. Both human raters and AI judges bring systematic biases to evaluations, and different AI models tend to favor different patterns. Being aware of those biases lets you interpret scores correctly and choose strategies, like using multiple judges or calibration, to reduce their impact. When a model evaluates candidate replies using its own probability estimates, it tends to score the answers it would generate more highly. This is called self-bias. Zhang et al. 2023 quantified this effect. GPT-4 preferred its own outputs about 10% more often, while Claude V1 showed roughly a 25% self-preference, so self-evaluation can overstate a model's quality. Many AI models tend to favor the first option they see, whether in pairwise comparisons or lists. You can mitigate this by repeating the same test with different orderings or using prompts that randomize or balance positions. This behavior contrasts with humans, who typically show recency bias and favor the last item they saw. Automated judges can show a verbosity bias, favoring longer replies even if they're wrong. Wu and Aji, 2023, found GPT-4 and Claude. One preferred 100-word answers with factual errors over shorter, correct 50-word answers, and Saito et al. 2023 saw a strong preference for the longer creative response when one reply was roughly twice as long. Subsequent work, Zhang and Saito, shows GPT-4 is less prone to this than GPT 3.5, suggesting the bias may shrink as models get stronger. Using a proprietary model as a judge requires sending your data to the provider, which creates privacy and intellectual property exposure. If the provider doesn't disclose their training data, you can't verify whether the judge is safe for commercial use or whether it relies on third-party content that could cause IP issues. Although AI-as-Judge has clear advantages and is likely to be adopted more widely, it has important limitations. To ensure reliability and fairness, we should supplement AI judgments with exact evaluation metrics and targeted human review where needed. We'll define which kinds of models are suitable to act as judges for automated evaluations and preview the main trade-offs: accuracy, calibration, and practicality. This sets up criteria we'll use to compare different model classes in the next sections. If the judge is stronger than the model, it can spot subtle errors, but may also reject outputs the model couldn't plausibly produce, making progress look harder. A weaker judge may let flawed outputs pass and overestimate quality. When judge and model are similar, evaluations are more balanced, but both can share the same blind spots. Using a stronger model as the grader usually yields more reliable evaluations than the model being judged. Beyond more accurate scoring, a stronger judge can also teach weaker models, highlighting mistakes or suggesting improvements, so it helps them produce higher quality answers. Using the stronger model for every reply can be slow and expensive. A common pattern is to generate responses with a cheaper model and have a stronger model evaluate only a small percentage, say 1%, to check quality and guide improvements. When a stronger model is too slow for real-time use, run a faster model to generate immediate replies while the stronger model evaluates those replies in the background. If the strong model finds a poor response, take remedy action such as replacing it with the strong model's answer. The opposite pattern, strong model generates and weaker model evaluates, is also common. Putting the strongest model in the judge role creates two issues. First, it has no eligible judge itself. There is nothing stronger to evaluate it. Second, we need an independent evaluation method to decide which model truly is the strongest. Otherwise, the comparison becomes circular. Asking a model to judge its own output can introduce self-bias, so it may sound unreliable at first. Despite that, self-evaluation is a practical sanity check. If the model doubts its answer, treat that as a warning, and it can also nudge the model to revise and improve its response. Press et al. 2022. Go et al. 2023. Valmy-Kamet et al. 2023. This is a short transcript showing user question, an incorrect initial reply, an internal check, and a corrected reply. Notice the first response line gives 30, an obvious error, and the final response corrects it to 13. The block highlights an explicit self-critique step that caught the mistake. Treat the flow as model output self-check corrected output, which is useful when designing systems that verify and fix their own simple errors. This is an open question. Many argue that judging is easier than generating. Anyone can have an opinion about a song without being able to write one. So a weaker model might plausibly evaluate outputs from stronger model. However, whether that holds in practice depends on the task and requires careful empirical testing. Zhang et al. 2023 found that stronger models generally align better with human preference, so people tend to choose the most powerful models they can access. That experiment used general-purpose judges, though. An alternative is to train small, specialized judges that follow narrow criteria and explicit scoring systems. For narrowly defined judgments, these compact, task-specific judges can be more reliable than larger, general-purpose evaluators. AI judges can be tailored to different uses, so we get several specialized types. Three common examples are reward models, which assign numeric scores, reference-based judges, which compare outputs to examples or rules, and preference models, trained on human pairwise choices. A reward model is a learned function that gives a numeric score to outputs, representing how well they match human preferences. It's trained from comparison or rating data and then used to guide policy optimization, RLHF, or to evaluate candidate responses. A reward model takes a prompt and a candidate response and returns a numeric score that reflects how good or correct the response is for that prompt. These models are commonly used in RLHF to rank or supervise outputs. CAPI, Google, 2023, is a compact example that outputs a score between 0 and 1 and has about 360 million parameters, much smaller than typical foundation models. A reference-based judge scores a model output by comparing it against one or more gold reference answers using metrics like BLEU, ROUGE, or exact match. This gives objective, reproducible measurements when references cover the expected outputs. However, it can unfairly penalize correct, but phrased differently, or creative responses if the references are incomplete. A reference-based judge evaluates a generated response by comparing it to one or more reference responses and reports either a similarity metric or a relative quality score. BLERT, for example, scores a candidate reference pair to measure semantic and linguistic closeness. Prometheus uses prompt, generation, reference, rubric to produce a 1 to 5 quality rating, assuming the reference represents a perfect 5. A preference model maps options to a scalar score that reflects human judgments. It's trained from pairwise comparisons, ratings, or rankings so it can predict which option people would choose. Those scores become a learned reward signal used to compare and optimize policies or decision rules. A preference model takes a triple, prompt, response A, response B, and predicts which reply a human would prefer for that prompt. These models are crucial for aligning models to human values and for scalable evaluation. Examples include PandaLM and JudgeLM, and some models even provide a short rationale explaining their choice. This diagram shows a layered system with components and the relationships between them. Notice the major blocks, the arrows that show direction of data or control flow, and any grouping that suggests hierarchy or modular separation. As we proceed, we'll refer back to these components to explain how information moves through the system. This figure shows an example PandaLM interaction, a human prompt and 2 model-generated responses presented for side-by-side comparison. The image is adapted from Wang et al., 2023, and reformatted slightly for readability. Even with known limitations, using an AI as a judge is a flexible and effective pattern. Running the judge role on smaller, cheaper models cuts cost and makes the method practical at scale, so much so that colleagues who were skeptical are now adopting it in production workflows. Instead of treating AI purely as a judge, this approach borrows ideas from game design, define rules, objectives, and interacting agents. Framing AI within game-like environments helps us design incentives, test behaviors, and evaluate performance in a controlled, repeatable way. In this section, we'll learn how to compare ranking models using comparative evaluation, which metrics, experimental designs, and analyses reveal real differences. You'll see practical approaches, pairwise comparisons, listwise tests, and diagnostic checks that help choose the best model for your task. When we evaluate models, our goal is usually to choose the best one, not to publish scores. You can rank models in 2 ways. Pointwise evaluation gives each model a score and sorts them, while comparative evaluation directly compares models, pairwise or in tournaments, to reveal which is preferred. Pointwise evaluation treats each model on its own. You run the model, assign it a numerical score, and then order the models by those scores. Imagine judging dancers one at a time, giving each a score and picking the dancer with the highest score. Comparative evaluation means showing models side by side and asking evaluators which they prefer, then aggregating those choices to produce a ranking. A simple analogy is a dance contest. Judges pick their favorite dancer, and the dancer preferred by most judges ranks highest. When quality is subjective, people usually find it simpler to compare items than to give each one an absolute score. For example, listeners can more reliably pick which of 2 songs is better, while assigning individual scores requires interpreting a scale and often gives inconsistent results. Comparative evaluation, first used by Anthropic in 2021, ranks models by comparing their outputs head-to-head and aggregating which responses are preferred. LLM-as-a-Judge's chatbot Arena uses the same idea. Community members judge pairwise matchups, and the system converts those votes into leaderboard scores. Providers often ask users to compare two outputs shown side by side to judge which is better. Those outputs might come from different models or from the same model with different sampling settings. This direct comparison surfaces user preferences and helps pick the best variant in production. This screenshot shows a dictionary entry. Notice the clear structure: a headword, part of speech, and numbered definitions with example usage. Also pay attention to the note that the caption was automatically generated. Automated descriptions can miss details, so verify extracted fields when using such images for data or teaching. This figure shows examples where ChatGPT asks the user to place two outputs side by side for comparison. Pay attention to how that prompt highlights differences in tone, facts, or structure, so you can choose or combine the best parts. For each request, two or more models generate candidate responses. A human or AI evaluator then chooses the winner, and many developers permit ties, so equally good or equally poor drafts aren't decided at random. Some questions must be judged by objective correctness, not by popular preference. For example, asking whether cell phone radiation causes brain tumors and offering only yes or no lets preference-based voting override the true scientific evidence. Training on those signals can push a model toward wrong or misaligned behaviors. Asking the user to pick between two different model answers often creates frustration. If they queried the model because they didn't know the answer, being asked to choose undermines usefulness and damages trust. Preference-based comparisons only work when voters understand the task well enough to judge outputs. This makes them suitable when AI acts as an assistant, helping users speed up things they already know how to do, but unreliable when users ask AI to perform tasks they themselves can't evaluate. These two methods are often confused, but are different. In A/B testing, a user sees the output from just one candidate model, while in comparative evaluation, the user sees outputs from multiple models side by side, so they can directly compare them. When you compare two items, we call that single comparison a match. Doing this repeatedly across the data produces a series of matches. The full list is shown in Table 3.5 and is what we analyze next. This table is a simple chronological log of head-to-head matches between models. Each row lists the match number, the two models compared, and which one won. Such a history is what we use to count wins, build rankings, or feed into ranking methods like Yellow or tournament aggregation. The win rate is the probability that Model A is preferred over Model B. Compute it by counting all head-to-head matches between A and B and dividing the number of matches of wins by the total. That fraction expressed as a percentage is A's win rate. When only two models are compared, ranking is trivial. The model that wins more head-to-head ranks higher. With more models, however, the pairwise win rates interact and can produce cycles or unclear orderings. A 5x5 table of empirical win rates doesn't immediately show a single correct ranking. This table reports win rates from 1,000 head-to-head matches for each model pair. Notice some surprising patterns. Model 1 beats Model 2 strongly, 90%, but loses to Models 3, 4, and 5. Model 2, meanwhile, beats Models 3, 4, and 5 by large margins, yet loses badly to Model 1. Those results create an intransitive cycle, 1 greater than 2, 5 greater than 1. So you cannot order the 5 models meaningfully with a single linear ranking. We feed the comparative signals into a rating algorithm that converts those comparisons into a numeric score for each model. The models are then ordered by their scores to produce the final ranking. Comparative evaluation adapts rating systems from sports and gaming to rank AI models using pairwise comparisons. For example, LLM-as-a-Judge's chatbot Arena switched from Yellow to the Bradley, Terry model, after finding LO's results were sensitive to the order of evaluators and prompts. A ranking is correct if for every pair of models the one placed higher is more likely than not to win a head-to-head match against the lower one. In other words, if Model A ranks above Model B, users should prefer A over B in more than half of comparisons. Treat ranking as a predictive model. We compute an ordering from historical match outcomes and use it to forecast future match results. Because different algorithms can produce different rankings and there's no absolute ground truth, the meaningful measure is how well a ranking predicts later matches. My analysis of Chatbot Arena finds the produced ranking works well for model pairs with enough matches. Details are in the book's GitHub repo. In this section, we'll examine common difficulties when comparing models and systems. I'll highlight how differences in tasks, metrics, data, and experimental setup can bias results and what to watch for when interpreting claims. With point-wise evaluation, most of the work is designing the benchmark and metrics to surface the right signals. Computing scores and ranking single outputs is straightforward. Comparative evaluation is harder because you must both gather richer, often subjective signals and design reliable methods to compare and rank models. In the next slides, we'll walk through 3 common challenges you encounter with comparative evaluation. In this section, we'll identify common scalability bottlenecks, the parts of a system that prevent it from handling more load. We'll overview CPU, memory, I/O, contention, locks, and network limits, and how to recognize which one is dominant. Comparative evaluation is data-intensive because the number of model pairs grows roughly with the square of the number of models. In January 2024, LLM-as-a-Judge ran 244,000 pairwise comparisons across 57 models, but that works out to only about 153 comparisons for each model pair. That is a small sample given the many tasks and behaviors we want to evaluate in foundation models. Many ranking systems assume transitivity. If a ranks above B and B ranks above C, then a ranks above C. This lets the algorithm skip some pairwise comparisons. Once it's certain about A greater than B and B greater than C, it can infer A greater than C without directly comparing A and C. Yellow-style ratings rely on transitivity. If A beats B and B beats C, then A should beat C. Several recent papers point out this can fail for AI evaluation because human preferences are not always transitive. Also, comparisons can be non-transitive when different model pairs are judged by different evaluators or on different prompt sets, so pairwise outcomes don't always compose. Independent evaluation measures only the new model on its own, so you only need to evaluate that single system. Comparative evaluation requires testing the new model against existing models, which means evaluating multiple systems and can change the relative rankings of previously evaluated models. If your company trains a model on internal data, you usually can't use public leaderboards directly to compare it. To do a fair comparative evaluation, you'll need to collect your own signals and run a private leaderboard yourself, or pay a public leaderboard service to evaluate your model privately. Randomly pairing models waste comparisons because many pairs become decisive quickly. A good matching algorithm stops retesting settled pairs and instead chooses matches that will reduce the most uncertainty in the overall ranking, which dramatically lowers the number of matches needed. Now we examine how inconsistent standards and weak quality control practices create risks for users and regulators. I'll point out common problems and why they matter for safety, interoperability, and trust. LLM-as-a-Judge's chatbot Arena gathers comparative signals by letting anyone submit a prompt, then presenting 2 anonymous model responses for a head-to-head vote. Model names are revealed only after voting, which helps reduce brand bias and produces direct preference data from the community. This approach pulls together a wide range of signals, which makes it robust and relatively difficult to game. The trade-off is that without strict standards, it's hard to enforce consistent quality and control, so results can vary across sources. Anyone online can run prompts, yet there's no single standard for what makes one model response better than another. Volunteers evaluating outputs may skip thorough fact-checking, so they can unintentionally reward responses that sound good but are wrong. People's preferences differ. Some want polite, filtered replies, while others prefer unfiltered responses. Training on these signals helps models match real users, but it can also encourage unsafe outputs. For example, a user might downvote a model for refusing an inappropriate joke even though a developer would prefer that refusal. Malicious actors can also upvote toxic responses and skew the ranking data. When people evaluate models outside their normal workflows, their test prompts often don't reflect real usage. Evaluators usually use the first prompts that come to mind and rarely employ advanced prompting techniques, so the results can be unrepresentative of how models perform in practice. In the LLM-as-a-Judge chatbot arena collection of about 33,000 prompts, exactly 180 entries are the simple greetings hello or hi, which is roughly 0.55% of the set. That count ignores obvious variants like hello or hey, so short greetings likely make up a larger share. You also see many repeated brain teasers. For example, the riddle, X has 3 sisters, each has a brother. How many brothers does X have? Occurs 44 times, a sign of duplication and skew in prompt collections. Because simple prompts are easy for most models, they reduce the signal we get about relative performance. If an evaluation contains too many such prompts, it can pollute the rankings, make models look similar even when they differ, so include varied, discriminative prompts instead. A public leaderboard that doesn't allow adding retrieved documents into the model's context will often give a false impression of RAG performance. Generating fluent answers and retrieving the most relevant documents are different skills, so ranking based only on final responses can undervalue a system with a strong retrieval pipeline. One option is to force users to choose from preset prompts, but that limits real-world diversity. LLM-as-a-Judge instead accepts any user prompts, uses an internal model to identify which prompts are hard, and evaluates and ranks models only on those hard prompts, so the leaderboard stays comparable without losing coverage. One option is to rely only on evaluators we trust, by training them on clear comparison criteria or teaching them advanced prompting techniques. That gives higher quality judgments. Scale uses this for private comparative leaderboards, but it's expensive and sharply reduces how many comparisons you can collect. A practical approach is to surface comparative evaluation inside the user's workflow. For example, present 2 generated code snippets in the editor and let the user choose the better one. This is already common in chat/code tools. Remember, however, that non-expert users may not know which snippet is correct, so pair comparisons with tests, linters, or automated validations to help them make safe choices. Many users may not read both options and click randomly, which injects substantial noise into preference data. However, when a small fraction of users vote consistently for the superior model, their signal can be strong enough to overcome the noise and reveal which model is better. Teams sometimes use AI to evaluate outputs because it's consistent, fast, and scalable. However, AI usually doesn't match trained human experts for nuanced judgments, though it can be more reliable than random internet raters. Now we'll shift from comparing models against each other to measuring absolute performance against concrete standards. You'll learn what absolute metrics are, why they matter for real-world decisions, and how they change our evaluation approach. Comparative evaluation gives a ranking. It tells you which model is better, but not whether that model meets your requirements. In other words, knowing B greater than A leaves multiple possibilities. B might still be unusable, just slightly better, or clearly suitable for the task. We'll walk through those scenarios next. Begin by reading the problem statement carefully and deciding exactly what is given and what you must find. Pay attention to constraints, units, and any implicit assumptions before you try methods or calculations. Our tests show model B consistently outperforms model A. It has higher accuracy, fewer false positives, and handles edge cases more reliably. Model A shows lower accuracy and some systematic biases, so it needs significant improvement before we could trust it in production. Start by stating the problem clearly and deciding what success looks like. Collect the key facts, constraints, and any assumptions so your next steps target the right objective. Both models fail to meet our requirements, but for different reasons. Model A tends to overfit and miss edge cases, while Model B underfits and shows systematic bias. So we must inspect metrics and specific failure modes to decide how to fix them. This is the first step. Carefully read the problem, then write down the information you're given and exactly what you must find. Having a clear list of givens makes the next steps much easier. Both Model A and Model B show strong results on this task. Pick between them based on secondary criteria, for example, latency, cost, or particular failure cases, rather than raw accuracy alone. A single observation or metric usually won't settle competing explanations. Run targeted evaluations, different metrics, controlled experiments, or held-out data to collect evidence that supports or falsifies each scenario. A head-to-head win rate, 51%, doesn't automatically tell you B's resolve ticket rate. The impact depends on which tickets B wins. If wins are concentrated on hard cases near the decision boundary, a small win rate edge can convert many unresolved tickets. If wins are mostly on examples both models already handle, the resolved rate gain will be minimal. In short, you need to know the outcome distribution across ticket difficulty, ties, and overlap to translate a win rate into resolve percentage. When deciding whether to swap Model A for B, user preference is only part of the picture. We also must weigh costs and the expected performance uplift. And if we don't know how big that uplift will be, we can't do a proper cost-benefit analysis. For example, if B costs twice as much as A, a head-to-head comparison doesn't tell you whether the typical improvement is worth the extra expense. You need an estimate or distribution of the expected gain to decide. In this section, we'll look ahead at where comparative evaluation is headed and why it matters. We'll highlight emerging challenges, methodological advances, and directions that keep evaluations relevant as systems and data evolve. As models improve beyond the abilities of individual annotators, asking humans to assign absolute scores can become unreliable or impossible. But people often can tell which of two responses is better. So pairwise comparison remains a practical way to get useful feedback. The Llama 2 team observed this when models generated writing beyond top annotator skills. Comparative evaluation measures what matters, which output people prefer, instead of relying on fixed task scores. Because it compares outputs rather than chasing absolute scores, it stays useful as models keep improving and doesn't become solved like traditional benchmarks. Comparative evaluations are difficult to cheat because participants can't simply train on the exact reference data used for comparison. As a result, public comparative leaderboards, which measure systems head-to-head on held-out tests, are generally considered more trustworthy than other public rankings. Comparative evaluation can reveal differences between models that single metric tests often miss. Use it alongside offline benchmarks to strengthen your evaluations and pair it with A/B testing online to capture user-facing performance differences you might otherwise overlook. We'll review the key points and takeaways from this lesson. I will highlight the main results and the actions you should remember going forward. As models become more capable, the probability of rare but catastrophic failures rises, which makes robust evaluation essential. Because open-ended, powerful systems are difficult to assess automatically. Teams often use human reviewers for sanity checks and judgments. Yet this chapter focused on approaches to automatic evaluation and their trade-offs. Foundation models are harder to evaluate than traditional ML because they're large, often multimodal, exhibit emergent behaviors, and are used for broad human-facing tasks that narrow benchmarks can't capture. Many new evaluation methods are being developed, but investment and attention still lag behind model and application development, leaving evaluation under-resourced. Because many foundation models include a language component, we focus on language model metrics such as perplexity and cross-entropy. These metrics measure how surprised a model is by text. Lower values indicate better predictive fit and are useful for comparing models, detecting noisy or out-of-distribution data, and guiding pre-processing choices. In the next section, I'll show how to read these numbers and apply them to evaluation and data cleaning. This chapter presents 3 evaluation approaches: functional correctness, similarity scores, and using an AI model as a judge. The first 2 are objective. They rely on explicit checks or measurable similarity, while AI-as-Judge is subjective because scores depend on the model, prompt, and interpretation. Subjective scores reflect the specific judge used, so they only make sense in that judging context. Different AI judges can score the same quality very differently, and as those judges are updated, their judgments change, making them poor standalone benchmarks for tracking progress. Use AI judges as complementary signals and always supplement them with exact automated metrics, human evaluation, or both. You can either score models individually and rank by those scores, or rank models comparatively by asking which of 2 is better. Comparative evaluation, familiar from chess, is increasingly used in AI, but it and alignment processes both need preference signals, which are expensive to collect. Preference models are specialized AI judges trained to predict which response a user would prefer, reducing the need for human comparisons. People long relied on language model metrics and handcrafted similarity scores, but the idea of using AI itself as a judge took off once foundation models arrived. Now many teams are experimenting with integrating these models into evaluation pipelines. Our next chapter explains how to build a reliable pipeline for assessing open-ended applications. In December 2023, Greg Brockman suggested that carefully designed evaluation suites, evals, often give teams the guidance they need to improve and trust models. He's saying that targeted tests can replace many ad hoc experiments when deciding whether a model is ready or how to fix it. A 2023 A16Z study reported that only 6 out of 70 decision-makers evaluated models by word of mouth. That's a small fraction, suggesting most organizations use more formal evaluation methods and that informal recommendations play a limited role. This is an informal shorthand for a quick assessment of mood, fit, or the general atmosphere. What people mean when they say a vibe check. You use it to decide whether the context, group, or plan feels right before continuing. Fields medalist Terrence Tao said, GPT-01 felt like a mediocre but not entirely incompetent graduate student, and he guessed 1 or 2 more iterations might get AI to a competent graduate student level. People then joked that if only the brightest humans can judge models, we may soon lack qualified evaluators for future systems. I filtered GitHub repositories by requiring at least 500 stars and searching for the keywords LLM, GPT, generative, and transformer. To catch projects that the keyword search might miss, I also collected suggestions from the community via my website. Language modeling benchmarks often align with how models do on downstream tasks, yet they miss important factors. Task-specific data, training procedures, and alignment or prompting differences can cause real-world performance to diverge, and researchers are actively investigating these gaps. Tokens can be characters, words, or subwords. Shannon focused on characters. He described entropy as a statistical measure of how much information each letter produces on average. Equivalently, the minimum average number of binary digits, bits, needed per letter when encoded optimally. People often prefer the natural logarithm because it yields cleaner math rules than logs of other bases. For example, the derivative of ln x is simply 1/x, which makes differentiation and many algebraic manipulations, especially with the chain rule and continuous growth models, much easier. SFT, or supervised fine-tuning, is when we train a model on labeled examples to teach specific behaviors. RLHF, reinforcement learning from human feedback, uses human ratings or preferences to optimize a model's outputs. If those concepts are unfamiliar, go back to Chapter 2 for a clear, detailed explanation before proceeding. The entry numbered 10, titled Quantization, is discussed in detail in Chapter 7. If you need the full explanation or examples, consult that chapter. Here we'll only reference its main point when relevant. Many complex tasks have clear, measurable objectives, but current AI often can't solve them end-to-end, so we use AI to handle parts of a task. That creates a new problem. Judging a partial solution can be harder than judging the final outcome. For example, it's much easier to score a chess game by its result, win/lose/draw, than to evaluate whether a single move was the right one. Decide whether to normalize word forms or expand contractions when pre-processing. Treating variations like cats versus cat, or will not versus won't as one token, or many changes vocabulary size, token counts, and how well the model generalizes. A 10,000 element vector may sound large, but it's usually much smaller than the original raw data, for example, full token sequences or high-resolution images. An embedding compresses and organizes complex information into a compact vector space that preserves useful relationships, making similarity search, clustering, and downstream learning far more tractable. Some models produce embeddings for individual words instead of whole documents. Two classic methods are word2vec, Mikolov et al., and glove, Pennington et al., which learn dense vectors that capture semantic relationships and are widely used as input features in NLP pipelines. Don't confuse the label AI judge used here with deploying AI as an actual judge in a court of law. In this context, it refers to an automated evaluator or scoring component inside a system, not a legal decision maker. In 2017, I presented MEWR at a NeurIPS workshop, a method to evaluate machine translation automatically without reference text by leveraging stronger language models. I didn't pursue it further, but the idea showed that powerful LLMs could serve as automatic evaluators instead of relying only on human-written references. Evaluation work, such as human labeling, automated scoring, re-ranking, or running many candidate checks, can take the lion's share of a project's budget, sometimes more than generating responses. That reality should shape design choices. Reduce or sample expensive evaluations, use cheaper proxy metrics, and invest in tooling that lowers per-eval cost. Spot checking means eyeballing a few items for obvious problems. It's quick and informal, but can miss systematic issues and won't give reliable rates. Sampling uses a defined method to choose items so you can make statistical inferences and quantify uncertainty. Use sampling when you need trustworthy estimates. Saito and colleagues measured human choices and found a tendency to prefer longer responses. The effect exists, but it's fairly small, much weaker than other preferences we might observe. This technique is often called self-critique or self-ask. It means the model evaluates its own output and asks internal follow-up questions to find errors or missing steps before finalizing an answer. BLERT typically outputs values around -2.5 up to about 1.0, which is not an intuitive probability or quality scale. This shows a general issue with AI judges. Numeric ranges can be arbitrary, so you must calibrate or map scores to human judgments before interpreting them. A Likert scale asks people to rate their level of agreement or frequency on an ordered numeric scale, commonly from 1 to 5. It's a simple, reliable way to measure attitudes or opinions and to compare responses quantitatively. Chatbot Arena stopped using the yellow algorithm, but kept calling their ratings yellow by transforming Bradley, Terry scores. They first multiplied each score by 400 and added 1,000, then rescaled the whole set so that Llama 13B ended up with a score of 800, an arbitrary anchoring to make the numbers look familiar. As Chatbot Arena grew in popularity, attempts to manipulate its rankings became more common. No one admitted doing this to the author, but several model developers told him they're convinced competitors try to game the system, a perception that can undermine confidence in the leaderboard.